Hello, so today we're continuing talking about optimization, which means getting the best result for something you're looking at. So it doesn't always mean achieving a maximum value. Sometimes it's a matter of the optimal situation would be minimizing something. But when we're talking about maximum and minimum, we're talking about points on a graph where we have slopes of zero. So slopes of zero involve talking about the first derivative, because that is giving you your formula for rate of change or slope on a certain situation. So this is definitely involving derivative still, but you need a formula before you can start getting its derivative. So a very key topic here is a formula for distance. So you may be familiar already with the formula for distance. If not, I'm just going to show you how it's derived, because you need to be able to find this on your own. So to figure out the distance between 2 points, if they are straight up and down from each other, so if I'm on a grid and I have a point here and a point here, it's very easy to find how far apart they are. Or a point here and here, that's very easy as well. When you start angling and you have 2 points not straight across in a horizontal or vertical distance from each other, you need to apply, thinking of this as being a right triangle. And therefore we can use the Pythagorean theorem to figure out what is this distance. So that's the idea here. Let's say I'm looking at this point, and I'm curious how far apart are they from each other. Well, the idea is this point has certain coordinates. Let's say its x is called x1 and its y value is called y1. And this point over here, let's say its x value is x subscript 2 and its y value is y subscript 1. So when I'm talking about this distance, I'm going to create a triangle here, and therefore I need the two sides. I need this distance and this distance. So how far apart are these? Well, had there been numbers here, this would be so easy. If this were a 10, let's say, and this were a 2, how long is that side? It's 8. But that came from 10 minus 2, or x2 minus x1. Same idea here. How long is this? Well, it depends what these are. If this is 12 and this is 3, then I would minus these and I'd say this is 9. But that is the idea. The way I'm going to get this distance is y2 minus y1, and the way I'm going to get this distance is x2 minus x1. Those things should sound familiar. When you were doing the slope formula, you took 2 points. You took point 1 that had coordinates x1, y1. You took another point called point 2, which had coordinates x2, y2. So from there, you would find the slope, which was looking at your difference in heights, so minusing these, and looking at your differences in horizontal values, minusing these. So by the way, I would suggest today that first of all, you just listen to this video. Don't try and copy what I'm writing, and later go back and then jot yourself down some formulas and work through them yourself. So just kind of sit back and listen to start. So right now I'm looking for this, so I'm going to use small letter d to talk about that distance. So the way I'm going to get the distance is Pythagorean theorem. This squared plus this squared will equal this squared. So d squared is going to come from minusing these two y's, right? And squaring that distance and minusing those two x's. So it would come from x2 minus x1 squared plus y2 minus y1 squared. So that's kind of the formula for distance. In reality, I would square root this to find the distance. But knowing I'm going to get into derivatives in a minute, including a square root sign here is making my algebra work a little bit more difficult, because I would have to get rid of that square root sign, write it to the power of a half, and start using the chain rule. So this might be easier just to leave as is. If somebody actually wants a distance when I have some x's and y's to put in there, I can do that and then find the square root. So here's where we're going. That's the formula that we're typically going to use in looking at how to optimize distance problems. So the first one, we'll do a couple today. The first one is kind of a classic where they give you, so this scenario would be, so here let's call this example number 1. We will have a formula of a shape. So they will give you, let's say, this shape right here. Okay, so we know what about this shape? We know it's a parabola. The fact that it's written in this order does not prevent you from rearranging it to have a better idea of what's really going on. If I just rewrite this, I can immediately see what this thing is. It's a parabola opening downward that's been moved 6 up. So up here at 6, I now have this parabola, and that's kind of the idea. So what is the question asking? The question specifies if I'm at the point 0, 3. Okay, so this point right here, 0, 3. What point on the parabola will be closest to this? Well, there's an infinite number of points on this parabola. There's a point over here. Well, is that the closest point possible on this parabola to the given point? Probably not. There's this real obvious one right here, right? If I were up here, is this the closest a point on the parabola could ever be to this position? Maybe. Maybe there's a different one over here. Maybe right there. Maybe that's the closest point. So the idea of closest point means we're trying to minimize a distance. So I need to be able to create this formula using the information I have from here, and then after that I will find a derivative. So the idea then, what I'm doing is I do have 2 points. I have this point right here whose coordinates are 0, 3. So I'm going to call that point 1. Then I have some random point somewhere here on the parabola. I'll call that point 2. And any point has the coordinates x, y. Well, that's not very specific. So what do I know about this random point right here? All I know it's at some, right now, undetermined x value, but it has a definite height. Y has been defined for you. They've told you y is that value right there. So what would be smarter than saying that point is just called pxy would be saying that point is p with an x, and the y value, since that point is on this parabola, is given by 6 minus x squared. So now I have everything I need. I've got this idea of an x1, y1, and I'm going to change this to something more specific. I have an x2, y2. So if I want now a formula for distance of this particular situation, it's d squared equals minus your 2 x's, square it, minus your 2 y's. So here's my 2 x's right here. So I'm going to minus them. X minus 0, and I'm going to square it. Then the formula says do the same thing for your y's. So I'm going to minus my 2 y's. So 6 minus x squared minus the 3, and I'm going to square it. So in reality, I'm ready to go. If I want to find the derivative right now, I can. But look at this. Can this be eased up a little bit? Or simplified a little bit to make your ultimate work easier? Of course it can. So what is this really? This is x squared. I can put this 6 and this 3 together and have it as 3 minus x squared all squared. So I have another choice right now. Should I expand this and simplify it, or should I start finding derivatives? Which that would be the chain, power rule and chain rule and all sorts of stuff. Right now, this is such a basic formula. It is definitely to my advantage to simplify this first. So if I write everything out, I'm going to have my x squared plus, so if I expand this, 9 minus 6x squared plus x to the 4th. Combine all my like terms. I'm going to rearrange them from highest degree to lowest degree. I will have x to the 4 minus 5x squared plus 9. Well, this is looking best of all right now. So this is the formula for the distance squared of any point on that parabola to this given point. But what do I want to do? I want to not maximize the distance. I want to minimize it. A minimum point would have a slope of 0. So I need a formula for slope. Formula for slope means the derivative. So this is like y squared, right? This is your dependent variable. You in math must use implicit differentiation when you are getting the derivative of a dependent variable. So if you think back to our previous unit, the derivative of this, so use the power rule, you would get 2y, but then you had to follow it with y prime. Okay, I can do that, but I'm just going to use d now instead of the y. So next step, if I'm going to continue on then, I had my d squared, so the 2 came down in front. I have 2d d prime equals, okay, let me just put this up here, So derivative here would be 4 in front, so 4x cubed, 2 in front minus 10x, derivative of 9 is 0. So I'm trying to find the formula for slope. So next step, I'm going to divide by 2d. So now, what am I trying to do? This is the formula for slope. If I want this to be a minimum, you know the slope is 0. So this gets replaced with a 0. Okay, so this now becomes 0. Well, and what's on the bottom? Well, not a 0, it's probably a 1. So I'm not looking what value is going to make this undefined. I'm looking for, if this is slope, what value of x will make this equal 0. So I only consider the numerator. All right, so that's what I'm solving. 0 equals 4x cubed minus 10x. The best way typically to solve is factoring. So I'm going to take out a 2x. That leaves me x squared minus, leaves me 2x squared minus 5. So now I'm going to, you can continue on. What are my critical numbers? Well, from this factor, x would be 0. And if I isolated the x here and continued on, I'd have positive or negative 5 over 2. And I'm not going to rationalize that. I'm just going to leave it the way it is. So there's 3 possible values of x on this parabola that are giving me the potential for having a minimal distance. One of them would be a point that has an x value of 0. So remember that diagram. If I'm on this parabola and I have an x value of 0, if I put a 0 in here, right? If x is 0, what will the y value be? It would be 6. Yeah, the point 0.06 is on the parabola. So what distance is that? That's a distance of 3 units away from this key point. So that is the situation if x equals 0. How could I do that using my formula? There's my formula right here. If I want to determine the value of d squared when x is 0, a 0 goes here, a 0 goes here, that's all wiped out. So d squared is 9, so what's d? Positive or negative 3, but we're talking distance, so we're going to take the positive value. So using the formula, when x is 0, I see the distance from my key point is 3 units. But I better check this one out too. 5 over 2, I think that's like around positive or negative 1.6. So maybe it would be better to be over here on the x-axis somewhere at about 1.6. Maybe that point would be closer to this key point than this one was. So you now will take that root 5 over 2, put it back in here, and evaluate it. So I'm just going to skip ahead. That turns out to be, we get root 11 over 2, which is approximately 1.7 units. So what did I do? I put this positive or negative, both, root 5 over 2, back into your d squared formula. So now I'm going to be only 1.7 units away. So if I have this as an x value on the parabola, I am closer than I was using an x value of 0. So that's the point that wins. Actually, there's 2 of them. There was positive root 5 over 2 and negative root 5 over 2. So somewhere there's this point or maybe this point. They're closer to the key point than this one was. But if the question asked you for find the points that are closest, you're not quite done yet. You know the x value that you needed, but you now need to find the y value. So how do you find a y value? There you go. There's the formula for that parabola. I now would substitute back in root 5 over 2 here to find the points, the specific points that are going to be closest to the point 0, 3. So if I put root 5 over 2 in here, whether it's positive or whether it's negative, when I square it, it would just be 5 over 2. 5 over 2 is 2.5. So this says 6 minus 2.5, which is 3.5. So whether I use positive or negative root 5 over 2, that would be the y coordinate. So that would be your answers to finding the points that are closest to the point 0, 3 on that particular parabola. Okay, so that was one of the questions. Typically, in terms of a shape, that was minimizing distance. So now, that was kind of a static situation. Nothing was in motion. You had a parabola sitting there and you were wondering about what point is closest. The idea of calculus more involves things in motion. And things in motion are only where they are for a split second, because a second later they've moved. So we have another look at a situation where things are in motion. So as soon as we're talking about motion, we're considering velocity and time and distance. So do remember that classic, right, formula for distance. It can be manipulated. I can isolate time or I can isolate velocity, and it does make sense. If you tell me I'm going 100 kilometers an hour for 2 hours, how far have I gone? Well, my velocity times my hours, and units are very important in calculus. So distance, velocity is 100 kilometers per hour times my time, which is 2 hours. Units cancel, so you're left with your quantity of distance, which would be 100 kilometers. So keep that in mind. So here is a classic question. Two things in motion, two vehicles, two people on a bike, two planes, and at some point, typically this is used for situations where you could have an accident, right? If these things came approaching each other closer than they should at a certain point in time. So this would be a situation, let's say it's noon and you have two planes traveling. Plane number 1 is going straight south or due south at 400 kilometers per hour. Okay, plane number 2 is, let's see, and this guy here, he's going south and he's located 200 kilometers north of plane number 2. Okay, so plane number 1 is traveling south, so going, it's noon, he's going south, 400 kilometers an hour, but there's another plane. But this first plane is 200 kilometers north of this other plane. What's the other plane doing? This other plane is going east, and this other plane is going east at 500 kilometers an hour. So you need, absolutely, you want to place this information on an X and a Y grid. The idea is any location of these planes or people or bikes or anybody must be a value right on the y-axis and the x-axis. So you're not putting random points out here. You have to be here. So think about where each plane is going to go. One's traveling south. So I'm not going to start it here, because for it to travel south, that would mean I have a dot ending up here. So it's got to be here somewhere. So it's going to be a point somewhere here, and it's going south, but it's 200 kilometers north of another plane. Okay, this other plane's going east. So to be going east, right, which is, of course, we have our north, south, east, west, right? There's your directions. So the other one's going this way. So the other plane has to be located here. So thinking about this for a minute, here's the correct setup. Here's plane number 1. Here's plane number 2, because I'm addressing everything that it's saying here. So this plane is 200 kilometers north of plane 2. This is in motion this way. This one's in motion this way. So they're going to continue to stay on these lines. But right now at time 0, okay, when this whole situation starts, I've got them placed right here. But that's not going to stay that way for long. A second later, this one has moved down and this one has moved here. So all of a sudden a triangle has started. And then time goes by and maybe this is the triangle. And things keep happening until eventually, you know, the situation changes. So this is the start of this question. So, well, I haven't given you the question yet. So the first question will be, at what time of day are these planes the closest that they'll ever be? Are these planes closest to each other? You will be never be asked for, at what time of day are they farthest away from each other? Well, probably when one hits China and one is somewhere else. Like, that would be silly. But closest. Closest would mean we're trying to minimize their distance, right? At some point, maybe it was the scenario right here. Maybe this distance is closer than this distance. So again, we're looking at a distance formula. So this was the initial situation, but a certain time later. So this is later. I don't know exactly how much later. Now, here was the original, but here's where we're at now. This one is maybe here, and this one is maybe here. Okay, so at this situation, I have a triangle. So we're back to where we were in our first example. This is going to be, I need this distance, and I need this distance, and I will use the Pythagorean theorem and square it to get that distance. And I'm going to try and minimize d, this kind of the same way we previously did. So what do I know? I know what time is it right now? I would just call this time t. I can't say it's 2 minutes later. I can't say it's 3 minutes later. I can't say it's an hour later. So right now, I can't say anything, but I would just call the time t. That's as good as I can get right now. Originally, this was 200 kilometers. That's how far apart they originally were. But this plane has been in motion. And how long has it been in motion? T hours. I can't say anything but t hours. So how far has this gone in this little distance? Distance is velocity times time. So for this plane, its velocity was 400 kilometers per hour times t hours. So I'm left with the h is canceling, and my units are called 400 t kilometers. So this distance right here is 400 t. That's how far it's gone. I would much rather it say 50 kilometers, because if this has gone 50 kilometers and I knew the whole distance was 200, I could go 200 minus 50 and I could say this is 150, but I can't. All I know is this distance is 400 t, so I'm stuck with it. So what is this distance of my triangle? 200 minus this. That will give me this distance. So 200 minus 400 t. And how much is this distance? Well, the plane started here. So formula for distance for this plane is its velocity, which was 500 kilometers an hour, times the time, which was t hours. So your hours cancel. I have here for this plane, it's gone 500 t kilometers. But that is reality. That is how far this plane has gone. So I have everything I need now to use the Pythagorean theorem. This squared plus this squared equals this squared. So the setup is the longest part. The math here is going to be fairly easy. So continuing from there. Okay, so now I'm going to just take these sides and put them in for the Pythagorean theorem. So I have 500t squared plus 200 minus 400t squared is d squared. So our first example today, we simplified that. You know what, when your numbers kind of get larger, maybe simplifying isn't as easy. I mean, I could. So I'm just going to show you something different to do. I'm going to say, you know what, I'm just going to tackle this right now, and I'm going to find the derivative. I'm not going to expand first. So derivative of this side, I'm going to have this 2d prime. So chain rule, right? 2 comes out front. Keep the 500t, take 1 away, but follow it by the derivative of the inside, which is 500. Same thing, my connector is a plus. Bring your 2 in front. Keep this the way it was. Take 1 away from there, and now the derivative of this would be negative 400. So you will have to multiply things out. So this times this times this times t. So I'm going to have 2d prime. Actually, my next step, what would be smarter here, I do need to isolate this in a minute. So this 2d would come down here, and you would divide all of this by 2d. So that is now gone. There will always be 2's out front because they came from squaring something, and there will always be a 2 here. So just to ease up your work, get rid of those 2's. The idea is you factor 2's out from the top, and they cancel that too. So now all that's going to be left is that times that is 250,000 t, and then you're going to do some backwards multiplying here. You get minus 80,000 plus 160,000 t. This is over d. I can put my t's together here. Oh, sorry, this is gone. So I have d prime being 410,000 t minus 80,000 over d. So what do I want the slope to be? I want it to be 0. So I'm going to solve for the top. By the time I'm done, I will get 8 over 41 hours. So that's how long it's going to take, right, for the planes to be closest to each other they'll ever be. You could change this to a decimal. But if they asked for what time of day, okay, are these planes going to be closest together? A time of day is things like 2:36 p.m. So you're not going to be saying 8 over 41 p.m. So this needs to be changed to minutes so that you can incorporate it into a time. So the question started saying this is all happening at noon. So how are you going to move forward to give a time of day? So it's noon plus this amount of time. So you could do unit analysis. If this is hours, now I'm going to times it by the knowledge that there are 60 minutes per hour. So these cancel. I would work all this out and I get about 11.7 minutes, which I could say is about 12 minutes. So if this whole scenario started at noon, it's now taken 12 minutes for them to be closest together forever. What time of day is it? It's 12 noon plus this extra 12 p.m. So your statement, because you must end with a statement, is that they're closest together at 12:10. If somebody said then, oh, how close is that? Well, you have your formula for distance right here. How close are they at 12:12? You would take your 8 over 41, you would put it in here for t, you would put it in here for t, you would work this all out and square root it, and if you want to try that, you should get an answer of approximately 156 kilometers. So that's the closest that they will ever be together. Okay, so that was just 2 examples. So it takes time to set them up, and the planes won't always be straight up and down from each other. You could actually have a plane here, but maybe this one was over here. And there's a concern, right? As they're both in motion, could they possibly be in jeopardy of crashing? But as time moves on, this guy's maybe here, this one's maybe here. You will always still have a triangle. This will always be D. This will always be found by looking at your original distance minus how far they've gone, and then minimizing the process. So working through these will give you some practice with distance formula. This can be expanded to the next lesson or the next video, which will involve minimizing time as well. So you can check what your homework assignment was and do some practice on this. Thanks for listening.